Okay, probably it's time to get started. So I'm going to chair the talk today. Today, it's our great pleasure to have Professor Lessing Ying from Stanford University to speak in our mathematical data science seminar. This is a joint seminar for Penn State, Purdue, and UMD. Lessing Ying is a professor of mathematics at Stanford University, where he is also a member of the Institute for Computational and Mathematical Engineering. He specializes in scientific computing and numerical analysis. In particular, his research concerns the design of numerical algorithms for problems in scientific computing. Professor Ying has received his bachelor's degree in computer science and applied mathematics from Shanghai Jiao Tong University in 1998. He received his PhD from the Crown Institute at New York University in 2004 under the guidance of Daniel Sorin. Before joining Stanford in 2012, he was a postdoc at Caltech and a professor at UT Austin. Lessing Ying has received many prestigious awards, including a Sloan Fellowship in 2007, and as Career Award in 2009, the James Wilkinson Prize in Numerical Analysis and Scientific Computing in 2013, and a Silver Morningside Medal in 2016. Recently, Lessing was also an invited speaker at ICM 2022. Lessing's most recent research focusing on machine learning and quantum computing. Today, he's going to talk about quantum numerical analysis related to numerical linear algebra, numerical PDE, and machine learning problems. Let's welcome.
Okay, thanks for Haizhao for the introduction, and yeah, I'd like to thank the organizers for inviting me to give the opportunity to talk at this seminar. So today I'm going to talk about some recent work in quantum computing, and especially from the perspective of numerical analysis. And this is joint work with my two wonderful students, Haoya Li and also Hongkang Ni. Haoya is a student in the math department, Hongkang is a student at ICME. Okay, so recently we have seen on news on social media that there's a lot of development in quantum computing. So it started, in recent years, it started from some recent hardware developments. For example, starting from Google, IonQ, where we have a more and more realistic, more reliable quantum devices, even though they're still had a lot of noise, but it's much better than what we used to have. So this hardware development has inspired a lot of developments in the quantum algorithms. And in today's talk, I'm going to share with you some more recent experience with developing quantum algorithm and how the numerical analysis is going to help. So before I get started, let me first say a few words about the basics of the quantum computing and what these objects are and how do we actually do computation on quantum devices. So a quantum computer, and the basic building block is something called a qubit. Okay, one qubit is essentially as a physical device to represent the Hilbert space, which is two-dimensional Hilbert space C2. And in physics notation, we're going to use 0 bracket and 1 bracket. Can you see my mouse, Haizhao? Or anyone in the audience tell me that? Can you see my mouse? Oh no.
Yeah, we can see.
Yeah, okay, great. So 0 and 1 stand for two canonical basis vectors. So it's very important to realize that whenever it's in the bracket, 0 doesn't mean 0. 0 is a unit vector. Okay, that's for mathematicians. Usually this is where the confusion started. Okay, when we see 0, we always think about the origin or think about something like 0, but in physics notation, 0 bracket is really a unit vector. Okay, so when you put n qubits together, and the Hilbert space actually become a tensor product. So instead of C2, and now you have C2 tensor product n times with itself. So because tensor product is very good at creating the high dimensional spaces, so therefore the dimension is C to the power 2 to the power n. So you have exponential growth of dimensional space. Now, naming basis vector in this high dimensional space is actually not too difficult because you can think about how many n-bit strings you can create by using 0 and 1s, and that's 2 to the power n different strings. And each of the strings, these n-bit strings, will actually correspond to a basis vector. So therefore, the basis vector in this C to the power 2n dimensional space can be at least indexed by these n-bit binary strings. Now, given quantum qubits and the algorithm that one way to describe the quantum algorithm of qubits is something called a quantum circuit. So here I have a diagram here, is that on the left-hand side, you have a few lines which correspond to the incoming qubit. And then what you're going to do is that you're going to do some operation U on these qubits. And then what you have is output is some other quantum state. Now, often you're going to do some measurement on some of these quantum states. And sometimes you care about the measurement result, and sometimes you care about the remaining quantum state. Okay, I'll say a few words more about this. So this is like very simple. This is essentially a uniform framework for all the quantum computation. Now you may ask, what actually goes inside the quantum circuit? Well, what going inside some quantum circuit is something called quantum gates. Okay, so here I give you some example of the quantum gates. So the first gate is something called Hadamard gate, which denoted by H. This is a gate which working only on one single qubit. And it's a unitary matrix, and the unitary matrix is given by 1 over square root of 2, 1, 1, and 1 minus 1. So essentially, this is the operation of rotating by 45 degrees. So because we're working on Hilbert space, I mean, we can certainly rotate 45 degrees. Now, there are other many one qubit quantum gate. So that, for example, there are polygates denoted by X, Y, and Z. And in physics notation, this is denoted by sigma 1, sigma 2, sigma 3, but here we're going to use X, Y, Z to denote them. And there's also something called a phase gate, which we're going to use later on. This is really a diagonal matrix with 1 on the first slot and 1, 1 slot and I on the 2, 2 slot. And finally, you also see this gate called a NOT gate. This is really flip the two coordinates. So coordinate E1 become E2, so E1 become E2, E2 become E1 in the canonical basis. And in terms of physics notation, it's 0 basis vector become 1 basis vector and vice versa. And you see that X is actually exactly the same as a NOT, okay? Now, just having these single qubit gate is not enough because they're not going to be able to create something called entanglement. So what we really need to do is actually have something called a multi-qubit gate. And the most famous multi-qubit gate is of the form of the control gates, which is in this diagram here. So essentially what you do is that you're going to use the information of the first qubit. Now we have multiple qubits. So you're going to use information on the first qubit to control the calculation of the second and to the end, the last qubit. So what this means is if you translate into the linear algebra language, you get the matrix on the right-hand side. What it essentially says is the following, is that if the first qubit is in the 0 state, okay, then you don't do anything to the rest of the qubits. On the other hand, if the first qubit is in the 1 state, what you're going to do is you're going to apply the matrix A to the remaining of the state, the remaining of the qubits. Okay. Now, a typical circuit now can take the following form. So the figure I have on the previous slide a little bit is too general, but now you can elaborate on this a little bit more. So typically what we have is two groups of qubits. One group of qubits is something called ancillar qubits. Here I denoted by 0M. So these ancillar qubits are typically in the simplest state, the 0 state, tensor product 0 state. They're kind of like they're kind of like registers or something like that, temporary storage space. Okay. Well, they're not continual working information, but they're going to be helping controlling the computation. Now, and then the second group of qubits is called working qubits, and denoted by phi here. And once you pass this big group of gates, at the end, you're going to do the measurement on the ancillar qubits, and you get a bunch of zeros or one on the ancillar qubit, and on the measurement, right? And the whole quantum state is going to collapse. So it's only the randomness, the quantumness is only on the remaining working qubits, and this is output. Then I denoted by output. Now, we ask that how much input information that the quantum circuit can handle. Well, the ancillar qubit doesn't contain any input information because it's all in 0. So the only information in the phi here. Now we know that a phi is actually a state belongs to the 2 to the power n dimensional space because I have a lowercase n working qubits. So therefore, the state phi can be written as a linear combination of these basis vectors, where each of the base vector is indexed by s, which is an n-bit string, okay, with some coefficient, complex coefficient cs in front of it. Now, since I have 2 to the power lowercase n basis vectors, so therefore this state can roughly encode capital N, which is equal to 2 to the power lowercase n complex numbers. Now there's a normalization because it has to be unit vector, but this number is roughly correct. Now, in order to do that, therefore the design, okay, so there contains an exponential amount of information, right? Because it's 2 to the power, it suddenly go from lowercase n, you go to the 2 to 2 to the power low case n. Now, when we talk about the complexity of the quantum circuit or quantum algorithm, typically we're measuring the number of gates in this capital U here. And what we want is that we want the U, capital U, the number of gates, to be polynomial in lowercase n. Okay, so because we want the number of gates to be proportional to the number of the working qubits, or maybe a polynomial of it. Now, because lowercase n is actually the log of capital N, so therefore the number of that complexity typically is something like a polylog n in terms of the amount of information that you feed into the quantum circuit. So this is why people believe that quantum circuit quantum algorithm can be more effective than the classical ones for the right problems. Now, I'd like to point out one thing is that so far I'm counting the number of gates, but in practice, it's actually the number of multi-qubit gates that's more important, because a single qubit gate is very easy to manufacture, relatively easy to manufacture, relatively easy to control. But on the other hand, and like this picture at the top, which is the control qubit gates, which is multi-qubit gate, these are the things which engineering is currently still challenged. Okay, so this is really a quick review of quantum computing. So now, so why do we need to talk about what's the relevance of numerical analysis to quantum computing? Well, the reason I believe is that it's like the fact that numerical analysis is related to the classical problem, is that because we have noise and which comes from device and noise and errors. So the quantum hardware is really partitioned currently into 3 categories. The first category called the NISQ, noisy intermediate quantum scale. So these are the algorithm quantum devices which has moderate size, like the second-more quantum chip that Google produced back a few years ago. They have about maybe 50 to the order of 100 quantum qubits. It's decent, but these qubits are very noisy. So that's why people call it a noisy intermediate scale quantum. Now, the device is better than that. What we call is early quantum fault tolerant. They have some fault tolerant capability, meaning that the qubits are quite reliable, but on the other hand, they still have quite a significant amount of noise. So the ideal situation is something called a fully quantum fault tolerant. So these are the quantum devices which is really reliable, and you can think about it. We can run them as if we run our laptop computer these days, right? So there you can more or less forget about the error. Yeah. So because the quantum devices is really have different stages, I think that in algorithm design we should really keep this in mind, and depend on which kind of devices you're working on, and we should care about the noise and error. And these noise and error come from 2 directions, come from 2 ways. One is that the device itself is not perfect; it has a lot of noise and error in it, and also on the other hand, when we do quantum algorithm, there's an inherent noise, and especially when you do the measurement, you only get you get a random variable, which in expectation is some quantity that you care about, and you also have to be very careful about the noise coming from the measurement. Now, I want to make an analogy with the classical algorithm. So in classical algorithm, when we teach, like for example, a sequence of numerical analysis classes, and including TCS classes, we care about approximation, interpolation, and quadrature. We also care about the numerical linear algebra, right? Because we want to solve linear system and nonlinear systems. We also care about ODEs and PDEs, and we care about the sampling. Now, the error, discretization error, and also computation error, and also stability error, for example, appear in any of these topics, right? And so therefore, the classical numerical analysis is designed to handle the error of these fundamental building blocks. On the quantum side, we also have a sequence of important quantum algorithms serving as building blocks. And the list is growing, and we don't know, it has not stabilized. But we know some of the members, like quantum phase estimation, quantum singular value decomposition, Fourier transform, and Hamiltonian simulation. And in all this, we have to handle error, we have to handle noise. And I advocate that there's also an area which is emerging called quantum numerical analysis, which is systematically study the noise in this algorithm and the problem in the algorithm in a careful way, and the goal is to produce more effective algorithms. So in this talk, I'll talk about 2 topics. First is quantum phase estimations, and second is quantum signal processing. And I will show you how numerical analysis can help in solving some of these problems. The first problem is called quantum phase estimation. So here's which typically called a QPE in the quantum community. So it's really a fundamental building block. what is the problem? The problem is that suppose someone hands you a unitary operator U working on n qubits. So this could be a very large unitary operator. And we're going to denote phi, bracket phi, to be the eigenvector of this unitary operator, and e to the power I lambda to be the eigenvalue. And this lambda is, here I do not say the eigenvalue, but you should really, more precisely, you should think about it's a phase, okay, of the eigenvalue. Now, the QPE problem is the following, is that suppose I hand you one eigenvector. Let's for the time being assume it's a perfect eigenvector of this big matrix U. And I want you to estimate what is a lambda, which is the phase of this eigenvalue. Now, the standard algorithm based on the quantum phase estimation is using something called a quantum Fourier transform. So here's a big circuit, which for the phase estimation using quantum Fourier transform. Now, but it does have some restrictions. So at least in the clean form, the algorithm assumes that the eigenvalue has somehow has a d-bit binary expansion with k0 and all the way to kd minus 1 denotes the 0, 1 values, which are different bits of this eigenvalue. Now, this obviously become quite restrictive, right? Because I mean, if I give you an eigenvalue, a big U matrix, and it's a priori I have no idea whether the eigenvalue should have this binary expansion, and I have no idea how many d bits I need, because in general I will need infinite number of bits. Now, there's one disadvantage of this algorithm is that it's even though it's very elegant, if you open textbook, you read about it, it's very elegant. But on the other hand, it requires a huge number of ancillary qubits. So it actually, the number of ancillary qubits d required is the same as the number of digits to use to represent this eigenvalue. Now, this poses a very serious problem for the quantum devices that we have right now. The reason is because, I mean, if you take a look at Google's Sycamore quantum chip, it has about like 60, 70 qubits. And if you want to represent the eigenvalue with high accuracy, you probably need about 30, 40 qubit to just represent this lambda. So meaning that ancillary qubits is going to take more than half of the total number of qubits. That's actually a quite waste for the precious quantum device that we have right now. Okay? So the second problem, I'm reiterating myself here, the second problem is that most of the eigenvalue does not have this binary expansion. How do we address this? How do we address this? The problem of the too many ancillary qubits. Well, the QPE with QFT, the quantum Fourier transform, is not the only algorithm to estimate the quantum phase. Well, there's an alternative. Is called something called Hadamard test. Well, the idea of the Hadamard test is just use this very simple circuit. Okay, compared to the circuit that I have on the previous slide, this is much simpler. So essentially, you only use one ancillary qubit, which is denoted by 0 here, and you have this 5 working qubits to store your eigenvector. And then the first thing you do is that you pass the ancillary qubits to the Hadamard gate, and then use a controlled U gate to operate on the 5, the working qubits, and then you do one more Hadamard transformation on the ancillary qubit, and then finally you do a measurement, and you check the probability of U get 0. So, well, let's just take a look at what does this circuit do, all right? Okay, because maybe not everyone is familiar with quantum computing in the audience, so it's a good exercise. So starting with a state which is denoted by 0 and 5, 0 stands for the first qubit, 5 stands for the rest of the qubits. We apply Hadamard. Hadamard is only applied to the first qubit. So 0 becomes 1 over square root of 2, 0 plus 1 over square root of 1. Okay, so this is what we get after we apply the Hadamard. And then we'll do the control qubit. So if the first qubit is 0, it doesn't do anything to the second one. But if the first qubit is actually 1, like what we have here, we see that we're going to apply the U rotation on the 5. So what we get is move the square root to 0, 5 plus 1 U5. Now if we do another Hadamard, let's see. What does Hadamard to do 0? Hadamard change 0 to 1 over square root of 2, 0, and 1. So therefore, the first part of the result we get so far is going to become 0, 5 plus 1, 5. And this 1 over 2 is absorb all the constants. Now the second part of the Hadamard is, and the Hadamard is also applied to this 1 here. But Hadamard change 1 to 0 and minus, so 1 over square root 2 in the 0 direction and the minus 1 over square root 2 in the 1 direction. So therefore, these two is actually coming from the second part what we have so far. Now, what I do next is just regroup it. Okay, so you see that it's equal to half of 0, 5 plus 5, and 1, 5 minus 0, 5. Now, then we're going to do measurement, right? Which we care about. I claim that we care about the probability of getting 0. Now, the probability of getting 0 in the measurement of the ancilla qubits is actually equal to the norm of this first component. So it's going to be phi plus u phi dot with phi plus u phi divided by 4. And 1 over 4 is come from the square of 1 over 2 here in the coefficient. If you do a little bit calculation, you see that this is the half plus 1 plus the real part of phi u phi. But what is phi u phi? Well, if you take a look at, because phi is an eigenvalue, but phi u phi is just e to the 2 pi I lambda, my phase, right? So therefore, you see that the probability of getting 0 is directly related to the phase. Now, but we don't directly have access to the probability of getting 0, right? Because when you do a measurement, you either get a 1 or you get a 0. So therefore, what you get is a random variable with mean, with the probability, with expectation P0. So therefore, in order to estimate the P0 accurately, what do you need to do? You need to repeat this experiment, this whole sequence, many, many times. So in order to get epsilon accuracy, you need to repeat 1 over epsilon squared times. And this is doable, but it's a little bit costly. Now, using a similar circuit, which just by acting this extra S dagger, which is this the adjoint of the phase gate, we'll get the measurement probability of getting 0 is actually related to the imaginary part of the phase. Okay, so therefore these two probability values, in fact, in expectation, give me my eigenvalue, which is e to the I phi, e to the 2 pi I phi. So as mentioned earlier, is that because we don't get direct access to the probability, so therefore in order to get epsilon accuracy, we need to try 1 over epsilon square repetitions, and this is quite costly. So the advantage of this Hadamard test is that the circuit is very short and very simple. It only uses 1 ancilla qubits, but the disadvantage is that the number of repetitions is way too high. Okay. Now, so but the 1 over 1 with epsilon is not the best we can do. In fact, in the literature, people have proven that there's a lower bound, which is something called Heisenberg limit, which said that instead you only need big O 1 over epsilon repetitions, or 1 over epsilon applications of U's, this gate, this circuit U, in order to get an epsilon accurate estimation of the phase factor. How do we do that? Well, to do that, let me mention another algorithm briefly, is something called a Kitaev algorithm. Well, Kitaev algorithm in the simplest form also assume that the eigenvalue has this d-bit expansion. But the rough idea of the Kitaev algorithm is that to estimate the K0, the first bit, the most significant bit, is going to use a circuit exactly the same as the Hadamard test. And then in order to estimate the relative bits, it's going to, for example, just J's bit, Kj, is actually going to use a circuit down here. But you see the difference is that instead of applying U only once, it's apply U actually 2 to the power J times. It's just can take the U and repeat it 2 to the power J times. And by doing some post-processing, pre-processing, and these circuits are going to effectively discover all these bits one by one. And the important thing is that since we're only discovering one single bit here, and the number of repetitions for each of these circuits is only actually constant. Okay? So therefore, the total cost is actually dominated by the complexity of the last circuit, which is the most expensive one. Now, but you see that the last bit is d to the minus 1. Okay, what is 2 to the power d to the minus 1? It's in fact is a resolution of your lambda representation. So it's exactly equal to 1 over epsilon. So therefore, the number of U's that you need to apply in the last circuit is in fact is equal to the Heisenberg limit, big O 1 over epsilon, and it only uses 1 ancilla qubit. Now the Hadamard test is the Kitaev algorithm is nice, very nice, but still has these two problems. One is that what if the eigenvalue does not have exact d-bit representation? What are we going to do? So the algorithm becomes less pleasant, but still more or less doable. And the other more severe problem is that what if, I mean, for all these algorithms I described, so what if my eigenvector phi is not in the exact eigenstate? It's in fact it has a lot of residues, has a lot of pollutions, and what are we going to do? So our approach is to present a very general setup. Okay, so we do not require our eigenvector phi to be aligned with any one single eigenvector direction. So, but we assume that it can have this phi is this expansion C0 phi 0 plus C1 phi 1 all the way to Cn minus 1 phi n minus 1. Okay, so now because this and we care about, for example, the eigenvalue associated with the direction phi eigenvector phi 0. Okay, the first one. Now, because it's not pure anymore, right? So what we do is that it's not aligned with eigenvectors. So what we do now is that if you apply the Hadamard test, things are less pleasant. So for example, if you calculate what is phi u phi, and through a bunch of calculation, you see that this is equal to C0 square, which is the coefficient of the first eigenmode square, times is the e to the eigenvalue of the first eigenmode, plus the summation of the energies and the remaining ones, which with their corresponding eigenvalues. So now, because we care about the C0, so we give it a special name. C0 square is we call it P0. So this is in fact is the energy of my eigenvector aligned with the first eigenvector, the one that I care about. The zeroth eigenvector, the one I care about. And the remaining energy is denoted by 1 minus P0. Okay. Now, I'd like to point out that our work extends, and one existing algorithm in the literature is called a robust phase estimation, which appeared first in these two papers. But these two papers does not directly handle the general case, but we generalize the algorithm to handle this general case where you have a dominant component in the direction you want to estimate, but you also allow energies in the rest of the directions. So the idea of our algorithm is very simple, is that compared to the Kitaev or quantum phase estimation, so we're not going to use bit-by-bit expansion anymore, because we feel that this is actually turned out to be restrict the way we think about the algorithm. So instead, what we do is that we keep a confidence interval. We took a more like a statistical approach. We keep a confidence interval for our eigenvalue. So in order to describe my algorithm, let me just first describe this picture here, which is really pure elementary geometry, but this is really the key of our algorithm. So we will require this P0, which is the energy C0 magnitude square, describe how our input eigenvector align with the first eigenvector, right? So we assume that it has to be bigger than 4 minus 2 square root of 3. So if you calculate what is square root of 3, it's 1.73, and so 2 times this is like 3.26, and like 3.46, and then you subtract this is something like 0.55 or something. Okay, so P0 is slightly bigger than 0.5. So here's a very important geometry. Let's think about this arrow here on the first figure. So this line here, the P0, this center of the circle essentially tells you that this is P0 times the eigenvalue I want. Okay, so if there's no noise, then my U phi u should get here. But because of the noise, measurement noise, and also this residual, and then my value is going to pollute it. So it's polluted by how much? It's polluted by 1 minus P0. This comes from the residual, and it comes from, and there's also some measurement noise, which I can control, but nevertheless, it's going to be noise. So therefore, the actual phase that I get is not aligned in this direction, P0, is actually in this cone here, right? Because P0 is the correct direction, and 1 minus P0 is how much I can deviate. So therefore, it's in this whole cone here. Okay. Now, how big can the cone be? So as I will show you on the previous slides, you will see that the biggest cone I can allow it to have is 2 pi over 3. So therefore, each of these angles here has to be 60 degrees on the right figure. So therefore, here I have some interesting number here. So this is 2 minus square root of 3, 4 minus 2 square root of 3, and 2 square root of 3 minus 3. So these are essentially the edges of the 60-degree triangle. And except that I require the hypotenuse plus 1 of the long edge. The long edge is actually equal to 1. So this is the calculation here. 4 minus 2 square root of 3 plus 2 square root of 3 minus 3 is equal to 1. So this is a special 60-degree angle. But what this says is that if P0 is bigger than this 4 minus 2 square root of 3, and then 1 minus P0 is going to be less than 2 square root of 3 minus 3, right? So therefore, I will be able to choose my measurement to be accurate. So it doesn't need to be all the way to epsilon, but I can make it to be reasonably accurate, such that I will have a confidence interval with this 60-degree angle. So in total, I have this 120-degree angle. Now I've mentioned 120 degree 2 pi over 3 many times, but why do we care about it? The reason is the following is that we know initially we have a confidence interval for our angle is 2 pi over 3. But now let's think about like what we did. Let's mimic what Kitaev did. Is that instead of using U, I'm going to use U squared. Now, if I apply U squared, what's going to happen is that you don't have the dominant one is not face the face theta 0, which is this 2 pi lambda 0 anymore. It's in fact twice of this because I have U squared now, right? So therefore, for the 2 theta 0, I have a confidence interval of 2 pi 3. Now, if you divide by 2, this means that I have a confidence interval for theta, which is equal to pi over 3, which is twice as small as the previous one. That's good news. But on the other hand, something is going to come to hurt us is because we're working on the unit circle, right? Because the phase is something which is periodic from 0 to 2 pi. So if I do know that the 2 theta 0, I do not know theta 0 uniquely because theta 0 can be shifted by a factor of pi, okay? So therefore, that's what I mean to something called a ghost subinterval. So if I get a 1 confidence interval for 2 theta 0, which is 2 pi over 3, if I divide by 2, I will have 2 confidence intervals for theta 0, right? They have each of them is going to shift with each other of distance pi. So this is how this figure is trying to show you, is that if I apply U0, I have this confidence interval, which is red of length 2 pi over 3. But then if I do computation for U2, I will have 2 confidence intervals. Each of them is pi over 3, and their distance pi apart. Now, you need to ask yourself, is that which one is correct? We need to ask which one is correct. Is this first one or the second one on the second level? Well, the only way for us to make the correct distinction is that here's one piece of information allows us to do that, is that the correct subconfidence interval on the new level has to overlap with the confidence interval on the previous level, because my true solution is in both confidence intervals, right? So therefore, you see that as long as now for the 2 confidence interval on the next level, the gap is exactly equal to 2 pi over 3, because that's pi minus pi over 3. So therefore, if my confidence interval on the previous level is at most 2 pi over 3, it will only intersect one of these 2 subintervals, right? So therefore, one of them is true, and the other one is a ghost one, which marked by purple here. So therefore, I can delete the ghost one because I do know that it does not intersect my confidence interval from the previous level. So you see that making sure that the confidence interval initially is less than 2 pi over 3 allow me to delete the ghost interval, confidently at every stage.
Can I ask a question?
Yeah.
So is this sort of, you're saying like if you iterate this unitary operator, then basically the Gershgorian circle is just tighter? Is that what you're trying to say?
No, it's not a Gershgorian cycle. It's always on the unit circle.
It's always...
Here is not, I'm not trying to say this Gershgorian cycle because this picture looks like a Gershgorian cycle. But once I estimate this angle here, I don't need this picture anymore. I only need a confidence interval in the radial direction.
Right, but the confidence interval, it's reminded me of sort of like what is your Gershgorian circle in a way, right? Is that good intuition or is that totally wrong?
It's slightly different, I would say. It's slightly different.
Okay.
Now, if we move to the next level using U to the power 4, we will have 4 intervals. Each of them has length pi over 6. And now, but you see that, but out of these 4, there's only one is good, right? But what we can do is that we can check which one of them is intersected with the right confidence from the previous level, which is this red one on the second level here. But in fact, there's only one of them intersect. So I know that this one is good, and the rest 3 are marked in purple. I can throw them away. So we can keep doing this, and this here I only show you 3 stages, but we can keep doing this until we have about log 1 of epsilon stages. And you see that every stage we're going to shrink the confidence interval by a factor of 2. So after this many stages, and the confidence interval is going to shrink all the way to size epsilon. So therefore with that. Now the circuit depth is actually equal to 2 to the power the number of stages. So it's 2 to the power log 1 of epsilon. So therefore it's the 1 of epsilon. Okay, so we reach the Heisenberg limit. Now I like to make one quick remark, is that what happens if my P0 is very close to 1? So previously I assumed that P0 is just greater than 0.54, right? And my algorithm works. But what if P0 is actually very close to 1? In fact, it's very good news, right? Because my input is very much aligned with the eigenvector that I want to estimate. So in this case, you see that the initial phase confidence interval can be much smaller, right? It's in fact because P0 is almost close to 1, so 1 minus P0 plus measured noise can be made quite small. So therefore, the initial confidence interval angle is in fact is proportional to 1 minus P0, which means that I started with a very, very small confidence interval. This tells me that if I want to reach epsilon accuracy, the number of stages I need is actually much smaller than log 1 of epsilon. So in fact, it's just log base 2 1 minus P0 of epsilon. So if a P0 is a small number, P0 is a number close to 1, 1 minus P0 is a small number. So this log is actually, this number of level J max is much smaller than log 1 of epsilon, what we had earlier. So therefore, the total number of circuit depths, as I highlighted here, has a prefactor 1 minus P0. So it's 1 minus P0 times over 1 epsilon. So now what this means is that if you can somehow prepare does this mean that algorithms are adaptive in the sense that if you can prepare your initial state very much aligned in the direction, the eigenvector direction, then the depth of circuit can be dramatically smaller. This is very useful for early fault-tolerant quantum devices. So okay, so let's consider a slightly harder problem. So far I've only considered one dominant eigenvalue, right? Eigenmode. What if my phi input can be represented as a linear combination of S dominant eigenmodes plus some residual, where each of the phi S satisfies this U phi S is equal to e to the 2 pi I lambda S phi S. So lambda S is my eigenvalue, my phase. Now, in order to be able to say that the first few ones are dominant, I will require that the energy CS square of the first few eigenmodes is greater or equal to some constant beta. And the basis beta is greater than omega, or rather W here, is equal to the amount of the total energy in the residual, right? So because otherwise I cannot say that the one that I care about is dominant. So that this is the line that's underscored in red is essentially said that the first few ones has more energy than the residual. Now the problem is to recover lambda 1 all the way to lambda S simultaneously. So before we do that, let's just take a look at what if we apply Hadamard, what do we get? So if we apply the Hadamard test, we get a phi U phi, and this is equal to now the summation of the energy of the first few eigenmodes, the square times their phase, plus the residual, okay? Now, if you take a look at this formula, I mean, if you worked in signal processing, you see that this formula itself tells me what? Tells me that this in fact is equal to the first Fourier mode of the following signal, which is Fs is equal to summation of S from 1 to S, and lambda S squared is my weight, and times the delta function, right? The delta function at the location lambda S plus the residual, right? Because the Fourier transform, the delta function becomes the plane wave, okay? So this is in fact evaluating the plane wave at the frequency 1. So you see that there's a clear connection between this phase estimation and this signal processing problem of trying to recover the bunch of deltas from the Fourier transform. Now, for one eigenvalue, you remember that we only need to do phi U phi to get the initial estimate, the confidence interval for my eigenvalue. But now I have capital S of them. So therefore, even to get the confidence in the initial confidence interval, having one Hadamard test is not enough, right? I need a little bit more because I need a bit more information to identify these lambda S locations roughly. So in fact, what we need is something poly in S, so roughly like S squared. So the capital K is roughly, you can think about S squared. And in this stage, in the first stage, I'm already going to do Hadamard test for U and U1, U0, U1, all the way to U capital K minus 1. If I do that, when you do the calculation, you see that this Hadamard test is actually going to give me all the Fourier modes of my lowercase f, which is a function at the top. There's a bunch of deltas, but not only at the first frequency, but at the frequency 1, 2, 3, all the way to K minus 1. Okay? So therefore, the initial problem, even at the first stage, becomes the following problem. I have noisy Fourier measurements, but I want to estimate the support of my the spike train. Okay, so this is a well-studied problem in the literature. It's called line spectral estimation problem. But however, all these algorithms in the literature, they assume that these eigenvalues have some gaps, sizable gaps. But in our problem, we don't want to assume that because we're trying to resolve my eigenvalue all lambda 1 all the way to lambda S to the resolution epsilon, which has independent of the capital value of capital S. So therefore, we have to develop our own algorithms. So we succeeded. We developed a new version of line spectral estimation algorithm that estimate all these eigenmodes, lambda 1, lambda 2, all the way to lambda S, So without any gap assumption, they could be as close as you like, with confidence interval of size big O of log 1 over beta minus W. So you see that beta over minus W is essentially my signal to noise ratio, okay? So this constant times 1 over K, where I will remind you that K is roughly S squared. Okay, so here's how the picture look like. So we're gonna start from the stage 1. In the stage 1, we have, so here I have 3 eigenvalues, lambda 1, lambda 2, lambda 3, I want to estimate. And I start from the stage 1, because my confidence interval has this size, which may be pretty big, which log 1 over beta minus W times 1 over K. So therefore, initially, I'm not going to be able to separate these all 3 eigenvalues. So my confidence interval will be merged into 2 confidence intervals. So I have 2. The first level I have 2, where the first one contains 2 eigenvalues, lambda 1, lambda 2, and the second one contains eigenvalue lambda 3. Now, then we can repeat this algorithm I described earlier by using higher power of U, right, my circuit. And you see that it's gonna split into smaller intervals, right? So this interval is each of this interval is gonna split into 4 intervals. And when I do more refined signal processing, and the second interval is gonna split into 2. But however, you see that a bunch of them is actually gonna be ghost intervals because they don't intersect with my true confidence interval on the previous level. So they can be deleted. So at the stage E1, I will end up with the 3 confidence intervals, and each of them is twice as small as the previous one on the previous level. Now we can repeat this process, and you get more small intervals on the next level. But again, most of them, in fact, 3/4 of them, 3/4 of them is in fact can be deleted because they're ghost intervals, and you only keep the one that intersect with my current interval, and so on and so forth. So you see that gradually we refine the location of lambda 1, lambda 2, lambda 3. And after log 1 of epsilon stages, we will have all the epsilon accuracy estimation for these eigenvalues. Now let me summarize this part. So I'm running already a little bit over time, but let me summarize this. So in this algorithm, we estimate multiple eigenvalues simultaneously. We consider both the case called a gapped and gapless case. So gap refers to the minimum gap between 2 adjacent eigenvalues, okay, on the real line. So obviously gapless case is harder because if you don't assume any gap, you have to resolve all the way to very fine resolution. So we also consider the so-called integer power and the real power. In the case of integer power, we only have access to our quantum circuit to the power j, where j is an integer. Where in the real power case, we can access u to any power r, which is real. So the second case is much more relevant if you do something called Hamiltonian simulation, where the u is actually come from Hamiltonian edge. And in this case, you can just tune the time r as a time to simulate u to the power r. Okay, so here's our result. We show that our quantum circuit works both for the gapless and the gapped case and the integer power and the real power case. So in the gapless case, which is more difficult one, the depth of our circuit and the complexity of a total cost is always big O of 1 over epsilon. This matches the Heisenberg limit. And in the gapped case, with a case which is a little bit easier, in fact, we get this nice omega over W over beta constant in front of the coefficient in front of it. Let me remind you, W is what? The W is the norm energy in the residual, and the beta is in the lower bound of the energy in each of the mode. So therefore, W over beta is essentially the noise to signal ratio, right? So if your noise to signal ratio is small, meaning that you have more signal, less noise, and then this omega over beta is actually a small constant, which means again, in this case, we'll be able to use a circuit which is much smaller, with a much smaller prefactor, if you get more pure data. Now, I'd like to mention that there's also a pure optimization approach developed by Ji and Ding and Lin at Berkeley recently, and they're using optimization approach, and the paper has attacked from the problem from a slightly different angle and obtained different results, but the scaling is similar, the Heisenberg limit. So in the remaining maybe 15 to 20 minutes, I will talk about something called a quantum signal processing. Okay, so this is something that I did about a little bit more than a year ago. Okay, so what is quantum signal processing? So quantum signal processing is try to address the following problem. So in quantum computing, typically, we only have unitary operators because the quantum evolution is unitary. But however, for many of the applications, we want to work with non-unitary operators. For example, Hermitian matrices. So a natural question appears is that given an n by n, capital N by n Hermitian matrix A, here we assume that L2 norm of the A is bounded by 1. So the question is that how do you represent a non-Hermitian matrix in quantum circuit? Well, the idea that people come up with the following is that we're going to use something for the block encoding. So let's use lowercase n again to denote the number of qubits required to represent A. So it's log base to capital N. Now, the block encoding essentially says that I'm not trying to represent A itself as a unitary operator because it's not. But what I can do is I can represent A as a top left block of a unitary operator. And I will denote the whole unitary operator by UA. Okay, there's a lot of work that goes into trying to how to represent this operator A using unitary in the block encoding. So with my students, again, Haoya and also Hong Kong, we have done some work is trying to represent pseudo differential operators using block encoding. Okay, but I don't have time to talk about that work today. So anyway, but having block encoding itself is not sufficient because often we want to do some work with our matrix A, right? We don't want to have access to the matrix A. We want to have some other function of FA of this matrix A. So here are some examples. One example is called Hamiltonian simulation, which essentially here A is going to be a Hamiltonian, and you want to do quantum Schrodinger evolution of it. Another important example is this 1 over x inverse. So this is so apply F to A is going to give you A inverse. So this is really solving linear system or do quantum machine learning, right? So an important question is to suppose someone give you a block encoding of the A. How do you compute a block encoding of FA? Okay. Now this problem is essentially solved by these sequence of papers. The first paper is by Low and Chang, 2017, and Killian and all wrote a nice paper extending this and making it more accessible. Because the first paper is in physics language, the second was in TCS and math language. The way to do that is the following: is that given me function fx, think about maybe it's like an inverse function, or maybe it's like a Hamiltonian simulation, an exponential function. What you're going to do is you're going to split it into two parts. One is called even part, the other is called odd part. And then what you're going to do is that you're going to apply the even part with an even degree polynomial, odd part with odd degree polynomial. And for each of the even and odd part, what you're going to do is that you're going to implement it with a circuit look like the following. So it actually requires only one, maybe two, but I mean, in this case, the simple case is just one extra ancillary qubits. So it's going to interlace this UA, this block encoding of my original operator A, with a bunch of circuit, which is called a control rotation circuit. So this CR, even though I use a big box of it, but in fact, it's just really control rotation. It's a very simple circuit. So, and this rotation angle is denoted by phi 0 all the way to phi d. The last one is phi 0, and the first one is phi d. Okay. Now, these two papers showed you that as long as you can find the right angle, this circuit will approximate my FA. Now, the question is, how do you find the angles, phi 0 to phi d? Well, to find the phi 0 to phi d, and this is actually turned out to be a harmonic analysis problems in the group of SU2. So there's a lot going to the details, but here I'm just telling you the end result is that in order to find this phase angle, what we need to do is the following: is that we need to work with this 2x2 function matrix, the function U, which is at every x is a 2x2 matrix. Okay, so it's a matrix valued function. So this matrix value function can be represented as follows in terms of these phase angles. This is phi 0 and phi 1 and phi d. And if you multiply these together, you will get this 2x2 matrix, which has polynomials p, x, and rx in it. Now, the problem is that you want to find this phi 0 to phi d such that the a function that your polynomial you're trying to approximate is in fact equal to the real part of this px, that one block. Okay, so what you want to do is that you want to find a bunch of angles when you multiply together, and you get a 2x2 matrix. And on the top left corner of this 2x2 matrix, and the real part is in fact the a that you care about. Okay, this is quite a long sequence of description, but anyway, so in the rest of the talk, it's convenient to write the p as a plus ic and the r as b plus id. Okay, so the question is that a given a, how do I be able to find a b and c and d? And once you find a b and c and d, you will be able to get the phase factors p0, p1, ppi. Okay. So now, typically, I mean, on the previous slide, it's written in terms of language as a polynomial interval from -1 to 1. But you know that whenever you have a polynomial from -1 to 1, you can lift on the unit circle by push it up and push it down, right? And then this polynomial essentially becomes the trig functions on unit circle. So this is what I'm trying to say here is that instead of studying, for example, the interval from -1 to 1, you can also push it onto unit circle, and then you really study a trig function with the parameter t here. And the problem that I described in the previous slide can be written in terms of these trig functions in terms of t in a much nicer form. And now you don't have this arc cosine comment. So you can go one step further, is that instead of write this as a trig function, you can also extend the trig function to extend the circle to analytic continuation to the whole plane, to complex plane. And so therefore, not only you have trig functions, you have the so-called Laurent polynomials, which involve the real and the positive and negative power of z. Let me just give you an example. Starting from the function fx equal to x, if you extend the trig extension, you get the function of ft is equal to cosine t. If you do this analytic continuation extension, it becomes fz is equal to z plus z inverse over 2. Okay. So the advantage of that, instead of working directly with polynomials, now I work with analytical functions. And usually we know that analytic function has much nicer property than polynomials. Okay, so this is a long introduction, but let's take a look at how do people solve it. So the first approach is proposed by Zagilian et al. It's from 2018. So what this paper does is the following, is that and also there's a follow-up paper by Har and Chow. And we are following the description of the Har here. So what it says is that we're going to choose a BZ, this B polynomial, right? This B polynomial, B here. So we're going to choose BZ arbitrary, and I'll say a few words about how to choose it. But once you choose BZ, you need to satisfy the condition that a squared plus b squared less than 1 on the unit circle. Now, then what you do is that you form this Laurent polynomial 1 minus b squared minus a squared minus b squared, and you study the roots of this polynomial inside the unit disk. It's guaranteed to have 2D roots, and let's denote by Cassi1 all the way to Cassi2D. If you compute the z minus Cassi I, multiply them together, and multiply by z to the power minus d, you'll have this special polynomial called E, Laurent polynomial called E. And this E will allow you to compute C and D easily, and I'm really, there's a lot of algebra going here, but for our purpose, we don't need to go into this. And once you have C and D and A and B, you can get P and Q, R. Once you find P and R, you can do a bunch of Fourier transform to figure out the phase factors. Okay, so that's the overall process. Now, this problem is that there's one problem, is that it has to go through these roots. And we know that, I mean, finding roots is not a very stable calculation. So in fact, they show that in order for this pipeline to work, and in fact, you need to do extended arithmetic computation. And in fact, the number cube and the number of bits in this root finding is d log d over epsilon. Now think about it, sometimes d could be as large as 10,000. Then you're not really doing 64 double precision calculation. You're actually doing tens of thousands of bits arithmetic. So this is obviously very expensive, very unpleasant. So there's an alternative approach which is advocated by the Lin-Lin's group at Berkeley, and they're using a purely optimization approach, and they get some very nice results. But the advantage of our algorithm is that there's no optimization involved, as I would tell you. So the method I'm going to propose is actually using something called a Pruni's method, which is the old method we developed hundreds of years ago by Pruni in France, and it's very well known in control and electron engineering literature, but somehow disappeared a bit in applied math education. So the idea is very simple, is that so we have this polynomial 1 minus a squared minus b squared Laurent polynomial inside the unit disk, and we want to find this easy. But if you take a look at the blue part is in fact is a characteristic function of the roots. Okay, so the idea is that instead of working with this 1 minus a squared b squared, I take a look at the reciprocal. I start with g, and if this g itself is what is that because it's reciprocal, so the roots become the poles, right? So therefore gz is in fact is equal to have this pole representation. This is pole representation. Now the question is that what can we say about the poles? In fact, you get a lot of information about the poles by just looking at the function value of g on the unit circle. So the idea is the following, that you can do a contour integral of gz along the unit circle, gamma is a unit circle, and then you do this, in fact, effectively corresponding to the Fourier transform of the function value on the circle. And in fact, you do the calculation, and you can show that g hat k, the case Fourier mode, is in fact equal to this, is minus summation of Cassi, all the Cassis, wj, and Cassi j to the power of k plus 1. Now, once you have that, what we can do is that we can collect all the negative Fourier modes together. So G minus 1, G minus 2, all the so on and so forth. And this actually corresponds to the sum of all the CJs raised to the corresponding power, multiply the weight of the residual Wj and take the sum. Why is this vector G hat minus useful? Well, to do that, I'm going to introduce a shift operator S. And what this shift operator is very nice, because let's consider each of the component of this G minus vector. So by that, I mean that I'm considering the vector CJ0, CJ1, all those so on and so forth. So if I apply S minus CJ onto this vector, as S essentially shifts everything upward by one slot. But CJ multiply everything by CJ. So it's effectively also increase the power by one slot, right? So therefore, S minus CJ applied to this vector is going to be equal to 0. Now, instead of using just S minus CJ, what I'm going to do is I'm going to take the product of all the I's inside the unit circle. Now, because S identity operator commute, so therefore this whole thing this is well defined, right? It doesn't depend on how you multiply the order of the sequence. So therefore, this whole product of S applied to this CJ vector is going to be equal to 0. Now, since it's applied to any CJ is equal to 0, if I do the linear combination of all the CJs, which give you G hat minus vector, that also equal to 0. So what does this mean? This means that if I apply this matrix polynomial, the product here to G hat minus is equal to 0. But this effectively is what? This is really the characteristic polynomial of all these roots, CZ1 all the way to CZ2D, but with Z replaced with S, okay? So therefore, this whole thing, which is equal to 0, can be written as MS, which is the characteristic polynomial applied to S, applied to G minus is equal to 0. Now, if you write out this one, using the fact that the S is a shift operator, you see that this gives me a relationship of these coefficients of the characteristic polynomial, M0, M2, M1, M2, all the way to M2D. So this is very nice because if I can form this matrix, obviously I can do because I can compute the Fourier integrals of this function G and then form this matrix. And then the null spaces, in fact, give me the coefficients of the characteristic polynomial. So the story here is that in order to calculate this E, which depends on the characteristic polynomial, I don't need to visit the roots. I can bypass all the roots calculation, which is very unstable. And using this null space calculation, using singular value decomposition, which is a very robust linear algebra routine, to get the characteristic polynomial directly. So let me skip this. So let me show you some results. So here's the example of the Hamiltonian simulation. So we run Hamiltonian simulation from 1,000 all the way to 5,000. And this tells you how the degree increases, goes all the way to about a 5,000 degree calculation. And it took about 100 seconds, even in the worst case, in the most expensive case. And the error is roughly about 10 to the minus 12. Let me also show you this most difficult case, which is called matrix inversion. So this is effectively the function 1 of x, right? So in fact, it approximates 1 of x very accurately until as long as it stay away from the interval, absolute value is bigger than 1 over kappa, where r kappa is a condition number. So here, sorry, this is a mistake here. This should not be kappa less than 50. In fact, we try all the way kappa into 1,000. So we try to do the matrix inversion problem with a condition number roughly like about 1,000. And you see that what happened to the degree? The degree actually grew quite rapidly. So for the problem of kappa equal to 1,000, and the degree is actually roughly about 50,000. So therefore, the highest degree, the longest phase sequence I need to calculate about 50,000. So in this case, we use various kind of state-of-art algorithms, including leverage the special properties of this Toeplitz matrix, and we get a fast algorithm for finding the phase. And you see that in this case is that the complexity is the total cost is roughly about 500 seconds or 400 seconds, and the error is roughly about 10 to minus 11. Okay, so this shows that in order to calculate these phase, we can just use the standard numerical linear algebra routines, and we can use the double arithmetic. There's no need to go to extended arithmetic. Okay. So this is all I want to say today. To conclude, so I talked about two things: quantum phase estimation and quantum signal processing. So I think that this is, especially for young people in the audience, I think this is a very exciting time for doing this kind of research and applying numerical analysis idea to quantum algorithm, because we're really experiencing a lot of developments in quantum hardware and the quantum algorithm and quantum software. And I think that for young people, this is an opportunity. Okay, finally, I would like to thank you for your attention. And my work is supported by National Science Foundation, DMS, and these are the related papers. Thank you.
Thank you very much for the excellent talk. Any question from the audience?
Hi, Lucy. If possible, maybe can you give a very quick comparison to lineage optimization approach?
Yeah, sure. I mean, lineage optimization approach is the lineage optimization approach is so you see that what we want to do is that we want to find this phase factor such that AX, you can see the slides, right?
Yeah.
Yeah. You remember what I said is that what do we want? We want to make sure that AX is equal to the real part of the 1-1 block of this matrix U, right? So what Lin's approach is, and his group's approach is essentially saying that